Now see here electromagnetic waves. So now see this chapter is actually based on 100% application of electromagnetic waves. We know we are using everyday television, mobile phones and so many other communication system. Everywhere we are using radio waves. So these radio waves are actually electromagnetic waves. So now here we have to discuss about how these waves are produced, what is the source of these type of the waves, what type of the energy are being carried by these type of the waves and their different types of properties and applications. So everything we have to study in this chapter. First here now in introductory part is here about electromagnetic waves. We know it, we have done in magnetism chapter. If you have got a current carrying conductor like this and I is flowing through this current carrying conductor, it has magnetic field around it. It means if there is electric field or electric current and around the electric current there is magnetic field. So electric current produces magnetic field around it. So Maxwell actually showed that for logical consistency, so that is a varying electric field or the changing electric field must produce magnetic field, and because it explains the the production of electromagnetic waves like radio waves, gamma rays or visible light, etc. So these are about the electromagnetic waves here. Now let us let us consider here about this thing is here charging of a capacitor. Suppose if you have taken a capacitor like this and capacitor has got the two plates, one is here positive and negative. This capacitor is being charged by using the time varying current here. So I is a function of t here. Now if you take this point and taking this point or this current carrying conductor, we make here an Amperian loop which is symmetrical one here and which is perpendicular to its plane is perpendicular to the electric current, and this is the suppose here the point P you are taking here. By using Ampere's circuital law, we can calculate magnetic field at this point, and we know it, that is here B dot dl is equal to mu naught I. So by using Ampere's circuital law, we can calculate the magnetic field at the point P. But if you take the another diagram here for this, and like this, if you have taken this is the plate, these are the plates, this is being charged and this is the plus and this is negative here, and you assume the loop here like this in this case. So when you are applying this one for this reason, you can get the magnetic field, but when you apply for this reason here, or you are taking in this manner, negative is here and taking the loop over here in this one. So you will find there is no current here. If there is no current here, you cannot get magnetic field, you cannot apply Ampere's circuital law. So you can apply Ampere's circuital law to this side, to the left of the plate, but to the right of the plate there is no application of the Ampere's circuital law, and we are only using Ampere's circuital law to calculate magnetic field. So this actually contradicts our this thing is here, because in Ampere's circuital law we know it, that is a B dot dl is equal to mu naught I. So for the left hand side here I is here, so we can, this term is here, but for this side the loop which is here, in this case this term is missing. So this part is 0 for these here. So this is the, there is actually contradiction of this application of Ampere's circuital law, but something is there in between the plates which is changing with the time as the current is changing or as the capacitor is being charged. So what is present inside the capacitor, now we have to see here. So now let us take capacitor here and see what is present between the plates of capacitor. So when the capacitor is being charged, there is a positive charge is being stored here and negative charges are here. But as the capacitor is charged being using the by using time varying current, there is electric field. And see this electric field E which is given here, E is equal to sigma upon epsilon naught. Sigma is the surface charge density of the plate, that can be written Q upon A epsilon naught. So, when you are charging the capacitor, electric field is changing with the time here. Because of this, electric field is changing and electric flux is also changing. So, we can write flux is equal to here E into A, and that we can write here Q upon A epsilon naught into A. This A and this A will get cancelled. So, we will be getting phi E is equal to Q by epsilon naught. Now, you differentiate with the time here this thing. So, when we differentiate with the time, we will be getting d phi E upon dt is equal to 1 upon epsilon naught dq upon dt, and we can write here in this case d phi E upon dt is equal to 1 upon epsilon naught I. This is called displacement current. So, we can write here ID is equal to epsilon naught d phi E upon dt. This ID is known as displacement current. So, when the capacitor is being charged, in the between the plates, electric field is changing with the time. As a result, electric flux is changing with the time, and because of the change in electric flux, current is there. That current is actually known as displacement current, and that is ID here. So, now we can write Ampere circuital law by explaining this one. That can be written here B dot dl is equal to mu naught IC plus ID, where IC is known as here the conduction current, and this can be also written mu naught IC plus, here we can write mu naught epsilon naught d phi E upon dt, and this equation is known as here Maxwell's Ampere equation. So, this is known as Maxwell Ampere equations. So, with the help of this theory, we can justify here this Ampere circuital law, and we can apply Ampere circuital law in this case also here. So, there is an introduction of actually this is the displacement current in electromagnetic waves.